Okay, another conic section is called a hyperbola. And I want to do a little bit of a review to build into the hyperbola. So here's what I'm talking about. Let's sketch a quick little circle. Of course, if you have a circle, that'll have a center point. Okay, if you put point P on that circle, we have some kind of distance right there. Okay, so I'll call that point 1. If I put another point right there, call that point 2. Okay, well that has the same distance. These two distances are the same. And if I put another one maybe right here, point 3, the distance to the center is the same. So no matter where you put a point, and that's what a circle is, it's all of the points that meet that requirement. All of those points have the same distance to the center. So one of the things we say about a circle is all of the points on that circle are the same. They have the same distance. So let me call it, I'll call that center C. So the distance CP1 is equal to distance CP2. Okay, so that's the characteristic of a circle. All of the points are the same distance to the center. Okay, that seems obvious. But then when we stretch that circle a little bit and make it an ellipse, so really what happens is you put a focus point there and a focus point there. Think of putting two nails in a board and then putting a loose string around those nails. And now I'm going to put my pencil inside that string and it will draw an ellipse around those two. Okay, so we still have a center, but see now all the points are not the same. If I put point 1 right there to the center, that point, if I put another point right here, maybe call this one point 2, see those distances are not the same. That distance to the center and that distance to that point, those are not the same like they are on a circle. Okay, there's a different relationship. These are called focuses. We have focus 1 and focus 2. Okay, here's the relationship. The distance from focus 1 to that point plus focus 2 to that point is always equal to the major axis all the way across. Now, a lot of times what we call the radius of that, we have a long radius and a short radius. Oftentimes we call the long radius A. And then there's a short radius also. See right here to there, that's the short radius. That's often called B. And then the distance from the center to the focus point is often called C. So the A is the long radius, B is the short radius, and C is the distance to the focus. Okay, so the way we write this now is this always happens. The focus, the distance from focus point 1, focus 1 to point 1, plus so that distance, that's this distance right here, F1 to P1, plus F2 to P1, that's this distance. We're adding those two distances together. Those two distances always equal 2A, or the major diameter. All the way across. Okay, so now it doesn't matter where you put the point. See, now if I put the point here, if I take this distance plus this distance, it equals all the way across. If I put a point out here, point 3, F3 plus F3 is equal to the major axis all the way across. Okay, so that's the definition. That's the formal definition of a circle. All the points are equal distance from the center. Formal definition of an ellipse. All of the points, when you add the points with their focuses, they always equal the long radius. It's called the major axis. Okay, then we did a parabola. Parabolas look something like this. They're satellite dishes. They're like TV antennas, and they have the focus point there and the center or the vertex right here. I'll call that C for center, or V. Maybe I should call it V for vertex. Okay. However far up the focus is, there's this another line under it that's called the directrix. And here's the formal definition of that. No matter where I put a point on this thing, I'll say I put the point right there. We'll call this point 1. That distance and then straight back down a right angle distance to the directrix are always the same. Those two are the same. So the focus, the distance focus F, focus to point, that distance is equal to the point directrix. That distance. And I'll call it 0.1 to the directrix. Those two distances are always the same. So if this thing looks like I need to flatten it out a little bit just to make it look right, let's say I put 0.2 way out here. Okay, that distance is equal to that distance. Those two things, those two lines are the same distance. That's the formal definition of a parabola. Okay, so those are the three that we've done so far. Okay, well, a hyperbola is the fourth one and the last one. So a hyperbola looks like this. A hyperbola, let's say we have, let me draw a grid. So here's a piece of graph paper. Okay, a hyperbola is it's kind of like two, it's not the same, it's not quite the same bend as a parabola, as a satellite dish, but it's gonna look like one. It can have well, it's gonna look something like this, and then the same over here, like that. And these are related. If I draw some kind of line through here, that's an asymptote. They're gonna all approach, they're both gonna approach the same asymptote, and likewise this way. They're gonna approach the same asymptote. So there are diagonal asymptotes here. Here's the formal definition. Let me call this the center again, right in the middle. I'll just put the center right in the middle. Okay, so here we call this a vertex and this a vertex. Okay, there's a focus point inside this curve. That's called focus 1, and this one over here, we'll call this one focus 2. So we've got a center, a vertex, and a couple focus points. So this is bugging me over here. I should be calling this one the vertex. Okay. It has something like this also. It has to do with distances and things to a point. So every single point on this one, so let's call this point 1. Okay, so I'm going to draw a line back to focus 1 and then a line over to focus 2, just like we did in the ellipse. Okay, so now the definition is point 1 to focus 1, that distance, minus 0.1 to focus 2, that distance. Now, you're supposed to take the larger one minus the smaller one, or you can just put it in absolute values. We want that positive version of that, so we subtract those two distances. Okay, now, just like before over here, the A number is the distance from the center to the major axis. Now, there's one more thing in here. I'll show you what this is in just a second, but this little distance right there is typically called A. So here's the diameter considered of a hyperbola, this distance. So when I subtract these two distances, it's equal to 2A again. That's the major axis or minor axis. Here I called it the major diameter. It could also be called the major axis. Okay, so this is one of the axes. Now, major implies that it's the longer one. So sometimes this is actually a shorter number than B. So instead of calling it the major axis, I'm going to call it the real axis, and I'll show you what that means in a second. There's a real axis and an imaginary one. Okay, think about a circle. and I'm going to stretch this circle. I'm going to pull it like this. And so if I pull it, it becomes an ellipse. And I'm going to stretch it even further. So I'm going to pull it even more. Think of like a rubber band, mathematically a rubber band. And we can just keep pulling it until it's super thin. But let's say we pull it mathematically so much that it breaks. As soon as we pull it so much that it breaks, it snaps open like this. And it becomes, so it went from an ellipse to a hyperbola. Ellipses and hyperbolas look very much the same. A hyperbola you can think just as a broken ellipse. So this ellipse right here, I could have drawn a box around it. Or this one right here, I could have drawn a box around it. And we have a major axis and a minor axis. Well, the major axis is how long the box is, and the minor axis is how wide the box is. So we have the same thing here. This ellipse that was in this box, when it broke, it is still in this box. Okay, so we have a major, actually that's not going to be the box. The box is going to be right here, but there's going to be a box. Okay, so this is the major axis, or the real one, because this is the one that's holding the hyperbola, and this is the imaginary one. Okay, so we have an imaginary axis and a major axis, and I'll help you understand here in a minute how to tell which one is which. Okay, that box, so here, that box for this particular one would look something like this, and we don't know how to get it yet, but we will. So just trust me for now, there's a box in there. Okay, this is the real one, and this is the imaginary one. So this is the imaginary axis, and this is the major the real axis, which is what I'm calling this one right here. Okay, but really what I want to emphasize is no matter where you put a point, if you subtract their two distances to the focus, it's always equal to that distance. So it could be even way over here. If I call this point 2, okay, the distance to that focus minus the distance to that focus, if I take those two distances and subtract them, I always get this distance. I get the distance between the two vertice points. Okay, that's what conic sections are trying to do. They're trying to describe a relationship no matter where you put a point on that shape, it fulfills one of these conditions. Okay, so what do these look like? Well, these are just like ellipses. So here's what an ellipse looked like if you don't, I'll just write it down again. It was x minus h all squared plus y minus k all squared over some kind of axis squared over some kind of other axis squared equals 1. It always had to be equal to 1. Okay, this is the same thing, only it's broken. It's x minus h all squared over over the x-axis. It's also y minus k all squared over the y-axis equals 1. We're going to force it to 1 again. So that looks exactly like an ellipse, except the ellipses had a plus in between there. A hyperbola is going to have a minus. Okay, that's how you can tell which way it's opening, either up and down or left and right. This one is opening up or down. Here's how you can tell. See this negative? The negative is on the y. That means the y-axis right here is going to have an imaginary vertex. There's like a vertex there, but it's imaginary. There's not really a dot there, but it exists in the math. It's the y-axis one. There's an imaginary one right there also. Those two imaginary ones help create the box, but the actual vertexes are on the x. There's literally a point right there and right there. So the x is positive, the x-axis is positive, the x-axis holds the vertex. If it's like this, y minus k all squared. Now this could be a or b. You could always leave it b. It doesn't matter. That just means the up and down stretch minus x minus h all squared. That just means the sideways stretch equals 1. Okay, this is a left or right opening. This one's going to look like this. I have these backwards, don't I? The y-axis, scratch that out. This is left or right. This one is up or down. Sorry about that. Here's how you can tell. The negative is on the x-axis. So this x-axis, there's a dot there, but it will not really exist. It's an imaginary dot. And the y-axis now, so the x-axis is now imaginary because it's negative. The y-axis, wherever that dot is going to be real. We're going to create a box out of that. The real ones are going to be the vertices. So there's the asymptote goes from corner to corner of these boxes. So we're going to draw some asymptotes corner to corner of that box. And the real one gets to be the vertex, the one that actually shows up. So that dot is actually part of the answer, and this dot is actually part of the answer, and that dot are not part of the answer. They just helped build the stretch. Okay, and then we're going to have to figure out how to get the focus point. And on a circle, we had a formula for the focus point. It was a squared minus b squared equals c squared. Okay, it's the same thing over here except the other way around. It's a squared plus b squared equals c squared. Okay, let's see if we can't make some of this stuff work. Let's try some. All right, here's our form. This is the stretch right here. Let me put that 1 over there. Okay, so here's the center. So the center of this thing, I'm going to call it C. Now they want the vertices. I'll show you what that is, the focus, and the equation of the asymptotes. Okay, well, so they're not really asking for the center, but we need the center to be able to get all of this stuff. So the center, so here's the x value. So the center is at 2, and we go to the 0, and here's the y value, -3. So there's the center point. I'm going to go ahead and just call that part of the answer. So 1, 2, 1, 2, 3. All right, now we have to get this little stretch thing, this box thing right here. Okay, that's what these are for. This is like the a squared number, this is like the b squared number. So I need the a and the b. Okay, the a is how wide the box is. So if we take the square root of this, I have a equals 1, and square root of that, we have b equals 2. Okay. The A is the Y on the y-axis. That's the Y stretch. That's the height of this box on the y-axis. So from the center, it's going up 1. So I have a dot there, and it's going down 1. I have a dot there. The x-axis is going to have a stretch of 2. So from the center, it's going 1, 2, and 1, 2. So I have this little box that I'm now going to draw. I'm going to draw a little box. This doesn't count as part of the answer. It's part of I'm going to make it a dashed line. It's not part of the answer. Okay, the asymptote goes through the corners. So it's going to hit this corner and that corner. So it's going 1, 2, up 1, 1, 2, up 1, 1, 2, up 1. So I know that the asymptote is going right here through the box, and the other asymptote is going right here. Okay, the x dot is imaginary. So this one on the x-axis going sideways, this one is imaginary, and this one is an imaginary. The ones that are real are the y dots. So this one is actually a point, and this one is actually a point, and then you just draw them into those asymptotes. And that's all you have to have for these kind of shapes. You don't have to have another point. Okay, so these are called the vertices. The vertices are that point and that point. So notice it's from the center, it's up 1 and down 1. So you could say, you could write it like this: from the center, then it was starting at -3, but it went up 1 and down 1, that would be okay. Or, of course, you can write it down twice. One of them, this dot right here, is at 2, -2. Well, see, that's -3 plus 1. And the other one, this dot right here, is at 2, -4. That's what -3 minus 1 is. I'm going to write it like this most of the time. Okay, the other two, these are also considered, so these are the real vertices, and then the imaginary vertices are these two. So I'm going to put another V, are these two. Starting at the 2, we went over 2. So see, starting at the 2, 2 minus 2 is at 0, so that's that dot right there, and 2 plus 2 is at 4. So that's saying 0 and 4, and then on the y, it was at -3. Okay, so there's check. We can check off the vertices. We actually have, let's go ahead and get the focus points also. So here's the focus relationship. So now this is a squared plus b squared is the c number. And I'll show you what c is in just a second. So a squared plus b squared equals c squared. Okay, so the a squared is 4. Well, one of them is 4. Since I'm adding, it doesn't matter which one is which. So the c number is the square root of 5. Okay, c is how far the focus point is from the center. So here's the center. The focus is always on the real axis. So the focus is always inside the curve. So it's square root of 5 up from the center, and it's square root of 5 down from the center. So the focus point is over 2, and then it's starting down 3, going up and down the square root of 5. And you can just answer it like that. The square root of 5 is about 2.2, so it's -3 up 1, 2.2, it's about right there, and it's -3 down 1, 2.2. It's about there. So there's a focus point, and there's a focus point. So remember what that's saying? This point right there, you don't have to do this, but I want to remind you, that distance minus that distance is equal to the real axis. It's how far apart the vertices are. It's equal to that. Those two things are, since we can count it, is equal to 2. Okay, check. We have the focus points. The asymptotes. We need the equation of an asymptote. Okay, I'm going to use point slope form. Y minus the y point equals slope x minus the x point. That one, remember that one? This one needs the slope and a point. It's called point slope form. Okay, this asymptote went through the center and that corner dot right there. So I can just count the slope. It's up, I need rise over run. So the slope is up 1, and it's over 2. So the slope is 1/2. Notice that's what the A and the B numbers are. Okay, and then I'm just going to use the center as a point. How about the center was at 2, -3. So this equation is y minus -3. So y plus 3 equals the slope 1/2 x minus the x point 2. Now, almost always, these are answered in y equals mx plus b form. So almost always you multiply this out. So if I do that, it's y plus 3 equals 1/2 x minus 1, and then I'll subtract the 3 over there. So it's y equals 1/2 x minus 4. Okay, that's this one. Now we need the other one. Well, the other one is exactly the same, except it has a negative slope, so I can just say plus and minus on the slope, and that's both of them. That's the equation of both asymptotes. Let's see, is that true? That is not true. You can't do that. We have to do it right here, plus and minus. So now if I take a negative 1/2 across there, this one is y plus 3 equals negative 1/2 x. Negative 1/2 times negative 2 is plus 1. And now when I move that one over there, y equals negative 1/2 x minus 2. That's the other one. I tell you what, let's just answer it like this so you don't have to, I'm fine, any kind of an equation will do. Now you can just say plus and minus, because one has a positive slope, one has a negative slope, and both of these go through the center. Okay, so here's what so check on the asymptote. So we need the vertices. So the vertices are this, the focus points, that's 2 focus points, and then let's forget about that and just answer it like this. So if you want to check your answer, if the answer key, I'm not sure, I'll have to check. I bet the answer key answers it like this, so if you want to check it, you might have to multiply it out and see if you have it right or not. Okay, let's do that again. Let's do another one. Okay, here's the center. The shift on the x is 0. The shift on the y is negative 2. So I already know the center. It's at 0, negative 2, right there. Okay. So on this particular one, the a is the square root of that, and the b is the square root of that. So that means on the x-axis, it's going over 2 from the center. 1, 2, 1, 2. On the y-axis, it's going over 2, up and down 2 from the center. 1, 2, 1, 2. Okay, that's my box. It's going to help build all of this stuff. So I know the asymptotes are going right through the corners of that box. This time the negative is on the y, so now this one is imaginary. The y dots are imaginary. So this is the real one, so it's going to use this one to approach the asymptotes. So this is a sideways hyperbola. Okay, so the vertices, these two. We started at the center, 0, negative 2, and went sideways 2. So I'll just say 0 plus or minus 2, down 2. That's that one, that's a vertice, and that one. Those are considered the vertices. And then the imaginary vertices, I'm going to call it vertice imaginary. Okay, it started at the center of 0, but then it went up and down 2 from the y. So that's at negative 2 plus or minus 2. So there are the real ones, there are the imaginary ones. Okay, check. Focus. It's a squared plus b squared equals c squared, and c is the distance to the focus. This time the focus is going to be sideways because the focus is always inside the shape. It's always on the real axis. So here the b squared number is 4. This squared number was 4. So c is the square root of 8, or 2 square roots of 2. Okay, so it's going sideways from the center. So the focus point, starting at 0, it's going positive and negative 2 square roots of 2, and then that focus dot is down 2. And last but not least, I need the asymptote. So I'm going to do this equation, y minus the y center, and then the slope, x minus the x center. Okay, I can just count the slope. The slope right there is from the center, it's going through that dot, it's going up 1, 2, and over 2. The slope is 2 over 2. Notice it was the a and the b. It's the y number over the x number. So the slope is 1. And then the center is at 0, negative 2. So we have y minus negative 2 is equal to the slope of plus or minus 1 times x minus 0. And there's both equations of the asymptote. Okay, let's see if we can't, let's turn it over. There's a couple more. So the only difference with these is they're not in that nice form. So we have to complete the square and get them in that nice form. So it's just like we were doing with ellipses. I'm going to rewrite all of the x's. Okay, 9x squared minus 18x. And I'm going to leave a little space. And then I've got a minus 4y squared and a minus 8y. Then I'm going to move the 31 to the other side. Okay, here first we have to divide out the 9, so now it's really x squared minus 2x. And here I need to divide out the negative 4. That leaves y squared. Now negative 8 divided by negative 4 is plus 2. Okay, now we can continue. Half of that's negative 1. Negative 1 times negative 1 is positive 1. So all together over here I added 9, so over here I have to add 9 to keep it balanced. Okay, cut this one in half is 1. 1 squared is 1. Now I have negative 4 times 1, so over here I added negative 4, so over here I'll add negative 4. Okay, here's the perfect square. We use that to get the perfect square. So I got that 9 on the outside and then x minus 1 all squared. Here I have a 4 on the outside and y plus 1 all squared. And 31 plus 9 is 40, minus 4 is 36. Okay, so when we take a look at the format, it has to equal 1 out there. So let's go ahead and divide off that 36. So I'm going to divide by 36, divide by 36, and divide by 36. So now we have 1. This 4 will reduce that down to a 9. So here I have y plus 1 all squared over 9. And that 9 will reduce that to a 4. So here we have x minus 1 all squared over 4. Okay, so the a number is 2. The b number is 3. See how this 3 is the rise number? The slope when we get the equation is the rise over the run. So I already know the slope is going to be 3 over 2. Okay, well let's start writing down some things that we have here. So here's the center. Positive 1, negative 1. Okay, positive 1, negative 1. Right there's the center. Now I need the box. The box is going to go on the x-axis sideways 2 and on the y-axis up and down 3. So sideways 2. That's what the x stretch number does, and the y stretch number is 3. 1, 2, 3, 1, 2, 3. So I'm going to build a box out of that. That box contains the corners, hold the asymptotes, so this is how wide this thing's going to open up. Okay, I can see down here that it is the y's that are imaginary. So that one is imaginary and that one is imaginary. The up and down ones are imaginary. So the vertex is right there and right there. So it's going to open sideways left and right through the real vertices. So there's the drawing. So the real vertices, they moved on the x-axis. So the center was 1, and then it went plus and minus sideways 2. And then the center was down 1. So there's the real ones. The vertices imaginary. Okay, the x part was 1, but now the y part of negative 1, we went up and down 3 from there. So there's the imaginary ones. Okay, my focus. The focus is a squared, that's that 4, plus b squared, that's the 9, equals c squared. So that's 13. So c is the square root of 13. That means the focus is the square root of 13 distance from the center. So my focus is right here and right here somewhere, and it's square root of 13 distance right here. That's about 3.5 units. 1, 2, 3.5. So the focus point on the x-axis, starting at 1, we went plus and minus root 13, down 1. There's both focus points. Okay, and then the equation of both asymptotes, y minus the y center. So I have my center, I should put my center up here so I can see it's still 1, -1. So it's y minus the y, so it'll be y plus 1 equals the slope, which I have down here is 3/2, so plus n minus 3/2 x minus the x center. And there is everything. Okay, let's try one more. Number 25. Okay, start out by grouping things. -25x squared plus 150x, leave a space, plus 4y squared. There's no more y's up there, so that's done. Equals, I'll take this 325 and put it on the other side. Okay, let me factor out the -25 here. That's going to leave x squared minus 6x with a whole. There's really nothing to do. That one is pretty much done. Here we'll go -3. -3 times -3 is +9. But it's really 25 times 9. 25 times 9. 225, so -25 times 9, so really I added a -225. Well, I have to add a -225 over here then. Okay, here's the completed square, so -25, x minus 3 squared. We didn't have to do anything to this one, plus 4y squared equals 100. Okay, it has to equal 1, so I got to divide by 100, divide by 100, divide by 100. So now this is 1. 4 will reduce that to 25, so we have y squared over 25. And 25 will reduce that down to a 4, so we have negative x minus 3 squared over 4. Okay, this is the imaginary axis. When we get to it, it's not going to touch the x, it's going to touch the y. Okay, so A is 2, B is 5. The A stretch is going to go sideways 2. It's going to go up and down 5. My center is right here. My center is at +3, and then there's no shift on that one, so it's at +3, 0. So I've got a center number at 3, 0. 1, 2, 3, 0. It's right there. The x's are going sideways 2. 1, 2, 1, 2. There's the imaginary vertices. The y's are going sideways up and down 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So this is a more of a stretched out box. Okay, the x's are imaginary because they were negative, so that one and that one are the imaginary ones. So the real ones, the real vertices are right here. So this one is going to use the real vertices, so it's going to go up and down. So those vertice points, it went up and down 5 from the center. So the real vertices, it went, so starting at 3 sideways, but then it went up and down 5. From 0. The imaginary ones started at 3, but it went sideways 2. So 3 plus and minus 2, 0. So that's those two vertices. Okay, my focus. It's b squared, it's this one squared plus the other one squared is equal to the c squared. So it's 29. So c is the square root of 29. That's about 5.5. Okay, the focus is always on the inside of the shape. So the focuses are going up and down 5.5 from the center. 1, 2, 3, 4, 5.5. It's actually not way up there. It's just a half point above those. Okay, so my focus point started at 3, and then from the 0, it went up and down square root of 29. So 0 plus and minus the square root of 29. Okay, and then the equation of the asymptotes, y minus 0, so I don't need to put that, equals the slope. Okay, you can count it, 1, 2, 3, 4, 5, it's rise 5 and run 2, or look, here was the rise number, 5, here's the run number 2, so it's plus and minus 5 over 2, and then x minus the x shift, 3. There they are. And that's how you do hyperbolas.